Okay. Okay. So, hi everyone. So, good afternoon. Good afternoon, all. Right. Okay. So, first of all, let me know whether audio and video everything clear. First of all, let me know whether audio and video everything clear. See, if it is not clear, please let me know here. If it is not clear, please let me know. Please give some comment in chat box if it is not clear. Right. Okay. Okay. So, we are dealing with the subject electromagnetics, and we are dealing with the magnetostatics. We are dealing with the topic magnetostatics. So, in magnetostatics, we have completed Lorentz force equation. So, next we have started with Biotin Source Law, right? Okay. So, we have started Biotin Source Law, right? So, the purpose of Biotin Source Law is to determine the small differential B field due to a small differential current element, right? Okay. So, all these things we have seen here, all these things we have seen, right? Okay. Okay. So, we have seen different applications of Biotin Source Law, right? So, we try to determine the B field due to a current carrying wire of finite length, and also we try to determine the B field due to a current carrying wire of infinite length, and also we have determined the B field at the center of a square loop and at the center of a hexagon and at the centroid of an equilateral triangle, right? Okay. And at the center of a circular loop, okay, and at the center of a semicircular loop, right? Okay. So, all these things we have seen here. So, all these are nothing but applications of what? Applications of Biotin Source Law only, right? And in the previous session we have determined the B field. We have determined the B field due to a current carrying wire. So, due to a current carrying circular loop here. So, if the current is flowing around this circular loop, then we try to determine some B field. We try to determine the B field at some point 0, 0, z. Understood? So, we have considered the radius of this circular loop as what? As rho, right? Okay. So, due to this current carrying circular loop, we try to determine the B field at some point 0, 0, z, and also I have asked to determine the B field at a point 0, 0, minus z. Okay. See, whether you determine the B field, at point 0, 0, z, or you determine the B field at 0, 0, minus z, you are going to get the same expression, and also the direction of B field is also what? Is also same. Why here? The direction of B field is going to depend upon what? Is going to depend upon how this current is circulating. Yes or no? See here, the current is circulating here in anti-clockwise direction. So, that means the B field is going to point in which direction? Upward direction, right? Okay. Okay. Alok Kumar, good afternoon. Good afternoon, Alok Kumar. So, I think you are absent yesterday, right? Okay. So, I hope you have gone through the previous lecture also. I hope so, right? Okay. So, the direction of B field will depend upon how the current is circulating around this wire. So, here the current is circulating in anti-clockwise direction. So, the B field is going to point in which direction? In upward direction, that is along Z direction. So, whether you take the point here, or 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 you take the point at the center. So, wherever you will take, the direction of B field is not going to change, because the direction of B field depends upon how this current is circulating. Okay. So, as you move from this point to this point, the current is not changing its direction. It is still flowing in anti-clockwise direction, and hence the B field direction, whether here or here, it is going to point in which direction? Positive Z direction. If suppose the current flows in clockwise direction here, if suppose the current flows in clockwise direction, then in that case, whether you consider this point or this point, the B field is going to point in which direction? Is going to point in negative Z direction. If the current flows in what? If the current flows in clockwise direction, right? Okay. Okay. And also we have determined the expression for B field here. So what is a B field we got here at this location? What is the B field we got? So B field is equal to mu I into rho square divided by what? Divided by I think 2 into rho square plus z square whole to the power of 3 by 2, right? Is this expression we got here? Yes or no? Okay, I think this is the expression we got here, right? So it will point in AZ cap direction. Okay, so if you put z equal to 0, if you put z is equal to 0, okay, that is at the center of the circular loop, put z is equal to 0, then you are going to get mu I rho square by 2 rho cube. So rho square will get cancelled, you are going to get the same expression. Yes, correct here, this expression is correct, right? Okay, so this is the expression we got for B field along the axis of what? Along the axis of the circular loop, right? Okay, okay here. So how we have determined here? How we have determined B field for all this type of problems here? We have applied what? We have applied the basic concept, that is the basic law, that is nothing but what? Biotin Source Law. Understood? So we have considered a small differential current element, and due to this small differential current element, we try to determine the B field, a small differential B field at this location. So we have seen that this small differential B field is having two components. One is what? One is along rho direction, and another one is along what? Another one is along Z direction. So for each and every current element, there exists what? There exists a symmetric current element on the opposite side. Yes or no? Exactly opposite to this one, there exists a symmetric current element. So due to this symmetric current element, what will happen here? So this current element is also going to have what? Rho component as well as what? Z component. Understood? So these rho components are parallel to what? Are parallel to this circular loop, and Z component is perpendicular to what? Is perpendicular to circular loop. Okay, so we have seen that these row components here, these row components that are parallel to what? That are parallel to circular loop will get what? Will get cancelled, and the components that are perpendicular to circular loop will get added up, and hence we got the resultant field direction is in which direction here? AZ cap direction, right? Okay. Paras moon, yes. So I think you have checked, right? Okay. So you are going to get the same result here, right? Okay. So if you check, if you are doing like that, it is very good here. After completion of class, if you have done or if you have checked how the B field at this location, okay, then it is very good here, because you will understand clearly how we have determined this B field at this point due to this circular loop. So that's what I am saying here. Once after completion of class, you have to practice each and everything whatever we have studied. So, and also you have to prepare proper notes here. So then only it is going to be very much helpful, very useful for your preparation. So otherwise, if you are simply learning and simply listening, means it won't help you here. Definitely it won't help you. Right, you may gain the knowledge, but you are not able to execute that knowledge in a right time. Understood? Okay, so you are not going to get good results. Okay, so if you don't write any notes, if you start again after 3 months or 4 months, then it will be like a new thing here. Understood? Again you have to start from scratch. So it is going to take more and more time. Understood? Okay, okay. So that's why I am saying you are listening the classes with interest. So what I am saying here is whenever you are listening, try to prepare the notes also. Okay, at the same time try to prepare the notes. So once the class is completed, you try to prepare the short notes and try to practice whatever we have studied in the class. Understood? Okay, so then only it is going to be effective and it is going to be useful, right? Okay, okay, yeah. Right. Okay. So Parasmoon, I hope you have done the same procedure and try to determine the B field at 0, 0, minus Z also. I hope so. Okay. So whenever you are deriving this expression again, so do you got any doubts here? If you are having any doubts, you can ask me here. You are free to ask. If you got any doubts, you can ask me. While determining the B field at 0, 0, minus z, right? Okay. So if you got any doubts, if you are having any doubts, you can ask me here. While doing the expression on your own, if you are getting any doubts, you can ask me. So that's what I am asking, right? Yes, Parasmoon. Okay. So if you say something, we will start next topic here. Once I start the new topic, then I cannot again come back to this one. Okay, no doubt. Yes, that's nice. That's nice here, right? Okay. So whenever you are revising, also you should not get most probably you should not get any doubts. Okay. If you at all getting any doubts, means you can ask me in the next class itself. Understood? Okay. Don't hesitate to ask any doubts here. Right. Okay. So next we will start next topic, that is Amperes law. So next topic we will start Amperes law. Okay. See, I am seeing regular students Alok Kumar, Parasmoon and Rahul Thakur, right? Okay. So today maybe Rahul Thakur is absent, right? Okay. Okay, Amperes law. See here. So what Amperes law says here is the circulation of B field, around any closed loop must be equal to mu times of current enclosed by that closed loop. So what is the statement of Amperes law here? The circulation of B field around any closed loop must be equal to what? Must be equal to mu times of current enclosed by that closed loop. Okay. See here, we have studied Gauss law here. Previously we have studied Gauss law, right? Okay. So in Gauss law, what I have told here, Gauss law for electric field, what I have told, the electric flux that is leaving any closed surface must be equal to what? Must be equal to charge enclosed by that closed surface divided by what? Divided by epsilon. So that means if you are having any closed surface, so this is closed surface. So if the electric flux is leaving, if the electric flux is leaving this closed surface, then if the electric flux is leaving this closed surface, means inside this closed surface there must be a source of what? There must be a source of that electric flux. So what is the source of electric flux here? So that is nothing but what? That is nothing but charge. And also this electric flux is going to depend upon what? Is going to depend upon the medium in which the charge is present. Understood? So the medium in which the charge is present. So that means it is going to depend upon what? Epsilon also. So the electric flux that is leaving any closed surface is depending upon charge it is enclosing, and divided by what? Divided by epsilon. That means the medium in which the charge is present. Understood? Okay. So this is what we have studied here. Then in order to get its differential form or point form, we have applied what? We have applied divergence theorem. We have applied divergence theorem. Understood? And then get the expressions in terms of point form or differential form. So in order to understand this Gauss law, you must understand the concept of what? The concept of flux and the concept of divergence. Yes or no? Okay. So these things I have already explained in the basics part. Understood? Now here, when coming to this magnetic field here, magnetic field in Amperes law, so you have to remember the circulation, how to represent the circulation of field around any closed loop, and you have to remember the Stokes theorem and all these things here. Okay. So here what is required here? What is required? So you have to understand how to represent the circulation of field around any closed loop. Already I have explained all these things here, right? Okay. How to represent the circulation of any vector field around any closed loop here? How to represent? So closed loop integral f bar dot dl bar. So this is any arbitrary field here, any arbitrary field I am considering. Okay. So the circulation of vector field around any closed loop you have to represent in this manner. Yes or no? Okay. So what do you mean by circulation and all these things I have explained already. Okay, see that basic part is very, very important here, coordinate systems and vector differential operator, so gradient, divergence, curl, okay, and this is circulation and flux, all these things are very, very important. So all these concepts I have explained in the previous sessions itself, right? Okay, so please go through that basics here. If you are strong in that basics, you won't face any problem while studying all these laws, right? Okay, so that's why I have spent that much of time in explaining those topics, right? Okay, yeah. So this is arbitrary, this is how you have to represent the circulation of the vector field around any closed loop. Understood? Okay, so that means here what you are determining here, what you are determining, how much of the given vector field, how much of the given vector field is lying or circulating around what? Around the closed loop. How much of the given vector field is aligned or lying along what? Along the closed loop, along the given closed loop. Understood? Okay, that's what you are measuring. Understood? Next, I have explained Stokes theorem also here. I have explained Stokes theorem also. So what is Stokes theorem here? We can convert this closed loop integral into what? Into surface integral. Yes or no? So closed loop integral can be converted into what here? Surface integral. And I have explained this Stokes theorem in detail in the basics itself, right? Okay, so you can represent this as what? Double integral curl of what? Curl of f bar dot what? F bar dot dA bar. So this is nothing but Stokes theorem. So you must have the minimum knowledge on what? On circulation of vector field around any closed loop, and you must know this Stokes theorem in order to understand Amperes law, right? Okay. Okay. So I hope you know all these things here, right? Okay. Okay. So now okay. Okay. Right. So what Amperes law says here is the circulation of B field, the circulation of B field around any closed loop, around any closed loop, around any closed loop must be equivalent to mu times of current, mu times of current enclosed by the loop or so mu times of current enclosed by the loop, or you can write mu times of current, penetrating through the surface, enclosed by the closed loop, Okay, so what is the statement of Amperes law? So the circulation of B field around any closed loop must be equivalent to what here? Must be equivalent to mu times of what? Mu times of current enclosed by that closed loop, Okay, so you have to write current enclosed by that closed loop. Okay, or you can say mu times of current penetrating through the surface enclosed by the closed loop. Okay, so both mean same here, current enclosed by the closed loop or the current penetrating through the surface enclosed by the closed loop, both mean same. Okay, So you have to understand that closed surface will always enclose the volume, and a closed loop is always enclose what? Always enclose a surface. Understood? So these things you have to understand here, right? Okay. So that's why the basics are very important here. Basics are very important. Okay. See, without the basics, it is not that much easy to understand this subject, right? Okay. Okay. So I'll give the mathematical form to this one, and I will explain what do you mean by this statement. Okay. So what this statement is saying here is the circulation of B field around any closed loop must be equivalent to mu times of current enclosed by the closed loop, or mu times of current penetrating through the surface enclosed by the closed loop. Okay. So that means here what it is saying here is we know how to represent the circulation of B field around any closed loop. How to represent here? So that is a closed loop integral B bar dot what? Dot dl bar. So this is how you have to represent what? You have to represent the circulation of B field, around any closed loop, Okay. So this is equivalent to what here? This is equivalent to mu times of what? Mu times of current enclosed, by the closed loop, or you can say mu times of current penetrating through the surface enclosed by that closed loop. Understood? Okay. So what do you mean by this statement here is, see here, if suppose in this region, let us assume in this region you are having B field here. Let us assume in this region you are having some B field. Understood? Now you want to determine how much of this B field. Here you are having some B field. Understood? Okay, let us assume you are having some B field. Now you want to determine how much of this B field is circulating, or how much of this B field is aligned around this closed loop, Understood? So I am choosing some arbitrary closed loop here. The loop is separate, field is separate. Remember that. Understood? So here B field is present. Let us assume here B field is present. Okay. So I am not representing that B field, right? Okay. Let's just assume there is a B field in this region. Now I have considered some arbitrary closed loop. Now I am enclosing this loop here. In anti-clockwise direction like this. I am enclosing this loop in anti-clockwise direction like this. Understood? Now I want to determine how much of the B field is aligned around this closed loop. That means I want to determine the circulation of B field around this closed loop, So if at all there exists any B field around this closed loop here, that means what here? Inside this closed loop there must be a source of what? B field. Yes or no? So you can compare it with Gauss law here. So in Gauss law what we have studied here, if you observe any electric field that is leaving the closed surface, that means if you are having any electric flux that is leaving the closed surface, then inside that closed surface there must be what? There must be a source of that what? Source of that field. The source of that electric field is nothing but what? Is nothing but charge. So similarly here, if you are having the circulation of B field around this closed loop, that means if any B field is aligned around this closed loop, means inside this closed loop there must be what? There must be a source of that B field. Now here what is the source of the B field here? The source of the B field is nothing but what? Is nothing but current. Yes or no? Okay. So the circulation of B field around this closed loop must be equal to what? Will be equal to what? Equal to the current enclosed by the closed loop. So if it is not enclosing any current, if this loop is not enclosing any current, that means if it is not enclosing any sources of B field, then you are not going to see any B field that is circulating around this closed loop. Okay. So source of electric field is nothing but charge, and the source of B field is nothing but what? Is nothing but current. Yes or no here? Okay, okay, yeah. So that means inside, if you are having the circulation for this one, if you are having circulation of B field around this closed loop is not equal to 0. So that means this loop must enclose what? Must enclose some current. This loop must enclose some current. So let us say the current is coming out of the board like this. Let us assume. So let us assume this is I1. Let us assume this is I1. Understood? So now in this case, what Amperes law is saying here is, if you are having, if the circulation of B field around any closed loop is not equal to 0 means this loop must enclose some what? Enclose some source of what? Source of B field, that is nothing but current. Understood? So circulation of B field around this closed loop is equal to what? Is equal to mu times of what? Mu times of what? Mu times of current. Mu times of current enclosed by the closed loop. Or I can say, see here, this loop is enclosing what? This loop is enclosing this surface area or not? This loop is enclosing this surface area, and this current is penetrating through this surface area. Current is penetrating through this surface area. See, current is coming out of the board. Yes or no? So that means it is penetrating through the surface area enclosed by this loop. Okay, so that's why I can write this as I enclosed, or I can write it as I penetrating. So what do you mean by I penetrating here? So this is the current that is penetrating through the surface, that is enclosed by what? That is enclosed by this closed loop. Okay, so every time I don't mention the current penetrating through the surface enclosed by the closed loop like that, I don't mention every time. So I will simply represent it as a current penetrating through the loop. So you have to understand, whenever I am saying current penetrating through the loop, you have to understand that this is the current that is penetrating through the surface that is enclosed by the closed loop. Understood? So this is what you have to understand, right? Parasmoon, what you are asking here? The periphery of loop is containing B field around the loop. What I am saying here? No, what I am saying is here. In this region, let us assume some B field is present here. Okay. Now, I am not worried about that B field. So, what I want to determine here is, I want to determine how much of this B field is aligned around some arbitrary closed loop. You can take any closed loop here. I want to determine how much of the B field is aligned around this closed loop. Okay. So, if any B field is aligned around this closed loop means there must be a source of that B field inside the closed loop. So the source of that B field is nothing but what? Is nothing but current. So that means this loop must enclose what? This loop must enclose some current. So then only you are going to have the circulation of B field around this closed loop. So that's what I am saying. Understood? Parasmoon, tell me here. See, if this loop is not enclosing any current element here, understood? So then you are not going to have any B field that is circulating around this loop. So if B field is circulating around this loop, or I can say how much of the B field, or you want to determine how much of the B field is aligned around this closed loop, if you want to determine that. Okay, so if there all exists any B field around this closed loop, then inside that closed loop there must be a source of what? Source of that B field. So that's what I am saying. Is it clear, Parasmoon? See, it is just like what? It is just like Gauss law here. You can compare with Gauss law. There we are dealing with closed surface. Here we are dealing with loops. There the source of electric flux is nothing but what? The source of field, the electric field is nothing but what? Charge. Here the source of B field is nothing but current. Right? Yes, Parasmoon, tell me here. Yes. Yes, here if you are having current element, what I am saying here is, if you are having current, right? If you are having current, right? So it is going to produce what? It is going to produce B field, obviously. So it is going to produce, the B field is going to circulate around this wire, yes or no? Here I am considering the current is pointing out of the board. So the current carrying wire is coming like this, understood? So the current is flowing out of the board direction. So whenever the current is flowing like this, the B field is going to what? Is going to circulate around this wire. The B field is going to circulate around this wire, right? Okay, so now if I want to determine the circulation of B field, I am considering some closed loop. I am considering some arbitrary shaped closed loop. Now if I want to determine how much of the B field is aligned around this closed loop, how much of the B field is aligned this closed loop, understood? So then how much of the B field that is aligned around this closed loop is equivalent to what? Is equivalent to mu times of current enclosed by this closed loop, understood? See, if there is no current here, understood, then you cannot see any B field that is aligned around this closed loop. That's what I am saying, right? Yes or no? Yeah, that's what Amperes law is saying, right? Okay. So if you are having any circulation of B field around this closed loop, means that loop must enclose what? That loop must enclose some current. So that's what Amperes law is saying. So is it understood here? Tell me here. Parasmoon. Right? Tell me here. Yes? Is it clear? Shiv Kumar, thank you sir for explaining. Okay, dear. Okay, so I hope it is clear here. I hope it is clear, right? Okay. So what Amperes law is saying here is the circulation of B field. If you are having any circulation of B field around any closed loop, okay, so this is equivalent to what? What is causing this circulation of B field around any closed loop is nothing but what? Is equivalent to mu times of what? Mu times of current enclosed by that closed loop, or you can say current penetrating through the surface that is enclosed by the closed loop. So both mean same here, both mean same, right? Parasmoon, that is the problem here, that is the problem. See here, I think you have not gone through my basic previous lectures. I think a del operator I have dealt, okay, then I have explained about gradient, I have explained about divergence. So there I have explained about flux, there I have explained about circulation, curl, each and everything I have explained here. So I think you have not gone through those lectures, right? So that's why you are getting these type of doubts. In my that's what I am saying here. First few lectures, okay, so first few lectures are very, very important. Coordinate systems, and then I have started with the del operator. So all these lectures are very, very important. If you have not gone through those lectures, please go through that lectures. So that's what I am saying, understood? Okay, see, I have already explained all these things here. So a closed surface is going to enclose a volume, and a closed loop is going to enclose the surface. So all these things I have explained very clearly, right? Okay. What I am saying here is this loop is enclosing this surface or not? Yes or no? Yeah? Understood? And this current is penetrating through this surface or not? So current penetrating through the surface that is enclosed by what? That is enclosed by this loop. So that's what I have said here. Understood? You can write mu into I enclosed, or you can write I penetrating. So that's what I have told, right? So I penetrating means the current is penetrating, the current that is penetrating through the surface that is enclosed by what? That is enclosed by this closed loop, right? Okay. Okay. Is it clear, Parasmoon? See, if you don't go through that basics, I am helpless here. I have already given each and everything here. Okay. So if you go through that basics, then it is going to be crystal clear here. Each and everything will be crystal clear. Understood? So without that basics, you will get, if I explain here also, then the next moment, if I explain some other thing, there also you are going to get the same doubts, right? Why means throughout the subject, whatever I have explained previously in the starting lectures, throughout the subjects, their application will be present. Understood? Okay. So if you don't understand those things clearly, then you cannot understand, you will get doubts here. Definitely you will get doubts, right? Okay. So that's what I am saying here. Please go through that lectures here. So they are very, 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 very important here, right? Okay. Okay. So the circulation of B field around any closed loop is equal to what? Mu into I enclosed, or current penetrating through the loop, current penetrating through the surface that is enclosed by the closed loop. So this is the statement here. Now see here. I am considering some loop here. I have considered some closed loop. Understood? Okay. Now here I am writing here I1, and here I2, right? And here I3, and here I3. Understood? So what Gauss law, Amperes law is saying, the circulation of B field around any closed loop is equivalent to what? Is equivalent to mu times of current penetrating through the surface enclosed by the closed loop. Okay. So what are the currents that are penetrating through this surface enclosed by closed loop here? I1 is penetrating out of the board, I2 is penetrating into the board, and I3 is penetrating out of the board. Understood? Or I can simply say the circulation of B field around this closed loop is equivalent to what? Mu times of current enclosed by the closed loop. What are the currents enclosed by the closed loop? That is nothing but I1, I2 and I3. Understood? Okay. So now tell me what is the circulation of B field around this closed loop here? So this is closed loop here. This is closed loop. Okay. Now tell me how to write Amperes law. Tell me the circulation of B field. I want to determine the circulation of B field around this closed loop. So that is equal to mu times of what? Mu times of current enclosed by the closed loop. Now what are the currents that are enclosed by the closed loop? Tell me here. That means you have to write I1 plus I2 plus I3, or I1 minus I2 minus I3, I1 minus I2 plus I3, like that here. So which combination you have to write? That's what I am saying. Okay. That's what I am asking, right? Whether you have to write I1 plus I2 plus I3, or I1 minus I2 plus I3. So like that. So what is the combination you are going to get? Tell me. We know that the currents enclosed by this loop are nothing but what? I1, I2, I3. We know that. Okay. What I am asking here is, you have to put here plus I1 or minus I1, and here you have to put plus I1 or minus I2. Here you have to put whether plus I3 or minus I3. So that's what I am asking, right? Tell me here. Tell me. Tell me here. Alok Kumar, are you there? I1 plus I3 minus I2. So I got one answer here. I1, okay, I1 plus I2 minus I3. So I got one answer from Parasmoon. Alok Kumar, tell me your answer here. Alok Kumar, are you there? Shivakumara. So give me your answers here. Tell me your answers. So I got one answer, that is I1 plus I2 minus I3. no, I1 plus I3 minus I2. Okay, I got I1. Okay, Parasmoon has told I1 minus I2 plus I3, right? Okay, so this is what Parasmoon has given. Alok Kumar is saying minus I1, right? Next plus I2 minus I3. Okay, so this is what Parasmoon is saying, right? Okay, now okay, this is closed loop 1 here. Let us consider this is closed loop 1. Next, see here. So I am giving another closed loop here. I am giving another closed loop. Let us say this is closed loop 2, right? Okay. Okay, yeah. So now see here. Now here I1, let us say I1 is pointing into the board, and here I2 is pointing out of the board, and I3 is pointing into the board. Now for this one here, for this one, tell me what is the circulation of B field? What is the circulation of B field around this closed loop? That is mu times of what? Mu times of, tell me for this one, for closed loop 2, what are the answers you are going to get? Tell me. What is the answer you are going to get for closed loop 2? I will explain here. I will explain how to write all these things. Okay. So first let me know your analysis. So for closed loop 2, what you are going to get? I1 plus I2 plus I3, or I1 minus I2 plus I3, like that. Okay. So what is the combination you are going to get? So which current you have to take as positive and which current you have to take as negative? Tell me here. Alok Kumar, Parasmoon, tell me. Tell me your answer for closed loop 2. For closed loop 2, I am asking. Tell me here. I have asked similar type of problem, na? Yes or no? Then why you are taking this much time? Alok Kumar is saying I2 minus I3 plus I1. So Alok Kumar is saying I2 minus I3, right? I2 minus I3 minus I1. So this is one answer I got. Okay. Parasmoon, what is your answer? Tell me. Mu times of. Tell me what is your answer. So for closed loop 2, I got this answer from Alok Kumar here. That is mu into I2 minus I3 minus I1. So Parasmoon, tell me here. Tell me your answer. Tell me here. Parasmoon. Okay. Okay, yaar. So what you are saying? Minus I1 plus I2 minus I3. Minus I1 plus I2 minus I3. Okay. Minus I1 plus I2 minus I3. So that means Alok Kumar has given this answer. Parasmoon has also given the same answer. Right. Okay. Parasmoon, you also got the same answer. Right. Okay. But here, see here. Here I think this is given by Parasmoon. Yes or no? You have given as I1 minus I2 plus I3. But here Alok Kumar has given as minus I1 plus I2 minus I3. Understood? Here both have given different answers. But here both have given the correct answer. that means correct answer means same answer. Okay, so that means you are having still confusion how to write this I1, I2 and I3, right? Okay, so I will tell you here, I will tell you how to write this I1, I2 and I3, right? Okay, so just remove all these things here, right? So I will explain here, I will explain how to write. See here, you have tried here, that is well, that is very good. Okay, okay, so I will tell you how to write the currents, how to write the currents. So circulation of B field around any closed loop is equal to what? Is equal to mu times of current enclosed, mu times of current enclosed by the closed loop. See, whenever you are writing the currents, how you have to write here is, see here, Ampere here, Ampere doesn't put any condition, Ampere doesn't put any condition how you have to enclose the closed loop. Ampere doesn't put any condition how you have to enclose the closed loop. So that means you can enclose the closed loop either in what? Either in anti-clockwise direction or clockwise direction, it doesn't matter. Okay, Ampere's law doesn't pose any condition how to enclose the loop. So that means you are free to choose or free to enclose the loop here. So that means you can enclose either in anti-clockwise direction or you can enclose the loop in clockwise direction. It doesn't matter. Okay, but while writing the currents, how you have to write? How you have to write? So that means what I am saying here is, whenever you are writing the currents, how you have to write? That means when you are going to get plus I1, when you are going to get minus I2, when you are going to get plus I3, like that. Okay, so how you have to write all those things? See here, if you consider I1 here, if you consider I1, so here I1 is pointing what? I1 is pointing out of the board. Understood? So if I1 is pointing out of the board, it is going to produce the B field in which direction here? It is going to produce the B field in anti-clockwise direction. Yes or no? So I1 is pointing out of the board means it is going to produce the B field in anti-clockwise direction. Understood? Okay, so now if the direction of B field produced by the current and the direction of loop you are enclosing, if both are same, then you have to consider that current element as what? Here, positive. See, what I am saying here is, if the direction of B field, produced by the current element and the direction of loop you are enclosing, if both are what? If both are same, then you have to consider that current element as what? Here, positive. Now if you consider here I1 here, I1 is pointing out of the board, so it is going to produce the B field in anti-clockwise direction. It is going to produce the B field in anti-clockwise direction. But here you are enclosing the loop in which direction? Clockwise direction. So that means the direction of loop and the direction of B field produced by I1, both are what? Both are opposite to one another. That means you have to consider I1 as what? Here, I1 as negative. Understood? So that means you have to write here minus I1. You have to write here minus I1. Next, if you consider I2 here, so I2 is flowing into the board. So that means it is going to produce the B field in which direction? Clockwise direction. Yes or no? And here the loop also I am enclosing in which direction? Here, clockwise direction. So the direction in which I am enclosing the loop and the direction in which this current element is producing the B field, both are what? Both are same. And hence I have to write here plus I2. Understood? Next, I3 here. I3 is pointing out of the board, so it is going to produce the B field in anti-clockwise direction, and here you are enclosing the loop in clockwise direction. So both are opposite. So that means you have to consider here minus I3. Understood? So in this manner you have to write the currents here. Right? Okay. So now tell me what is the answer you are going to get for second closed loop? Tell me. For this closed loop, what you are going to get? Tell me. Now tell me the answer here. Now you have to tell me the answer correctly. So what I am saying, whenever you are writing the current elements, how you have to write? You have to consider the direction of B field and also you have to consider the loop direction. So if both are what? If both are same, then you have to consider that current element as positive. If both are opposite, then you have to consider the current element as negative. Right? Okay, so now tell me the answer for this one here, for closed loop 2. For this one, tell me the answer. Tell me here. Now I am expecting the correct answer from both of you, right? Tell me here. Yes. Alok Kumar, tell me the answer for this one now, for closed loop 2. Tell me here. So Alok Kumar, Parasmoon. Now I am expecting the same and correct answer from both of you. Okay, so if anybody is there in chat, if anybody is there in live, okay, so please give your answers in chat box here. Please give your answers in chat box. So what you got? I2 minus I3 minus I1. Yes. The same answer or not? You are going to get the same answer, that is I2 minus I3 minus I1. The same answer you are going to get. Why here? What I have done here? I have changed the direction of current and also I have changed the direction of loop. Understood? I have changed both the things. So here I1 is pointing out of the board. Here I have taken I1 pointing into the board. Here I have taken I2 into the board. Here I have taken I2 out of the board. And here I have taken I3 out of the board. Here I3 I have taken into the board. And here I have enclosed the loop in clockwise direction, right? And here I have enclosed the loop in anti-clockwise direction. And hence you are going to get what? You are going to get the same result, right? Or if you want, you can check here. I1 is pointing into the board. I1 is pointing into the board. That means it is going to produce the B field in clockwise direction. But here you are enclosing the loop in anti-clockwise direction. So you have to write here minus I1. Next, if you consider I2, I2 is pointing out of the board and the B field is going to, the B field will be in which direction? In anti-clockwise direction, and here you are enclosing the loop also in anti-clockwise direction. So you are going to get what? You are going to get plus I2. You are going to get plus I2. Next, if you consider I3, I3 is pointing into the board and it is going to produce the B field in which direction here? In clockwise direction. But here you are enclosing the loop in which direction? Anti-clockwise direction. So that means you have to write I3 as what? Minus I3. Okay, so this is the way to write what? To write the Amperes law. This is the way to write the Amperes law. So I hope this is crystal clear here. I hope this is crystal clear, right? Okay, okay, okay. So, so you have understood how to write this Amperes law. So that is circulation of B field around any closed loop is equal to what? Mu times of I enclosed or or I penetrating, or I penetrating. Okay. Sorry, right? Okay. Now we try to represent the same expression. We try to represent the same Amperes law in terms of what? In terms of current density. In terms of current density. Understood? See, in Gauss law also, first what we have done here? We have determined, that means we have expressed the electric flux that is leaving any closed surface as what? As the net charge enclosed by the closed surface divided by what? Divided by epsilon. Next, what we have done here? We have represented this net charge as what? This net charge in terms of what? In terms of volume charge density. So that is, we have represented it as triple integral rho v dv divided by what? Divided by epsilon. So Q net we have represented in terms of what here? Charge density in this manner. Understood? So here also we try to represent this Amperes law in terms of what? In terms of current density. In terms of current density. Understood? Okay. Okay. So okay. So I can directly tell that this current can be represented in terms of what? In terms of current density as what? As Z bar dot dA bar double integral. So J bar units are nothing but what? Ampere per meter square, and this dA bar units are nothing but what? Meter square. So you are going to get what? You are going to get the current penetrating through the surface. Okay, so in this manner I can represent I. In this manner I can represent the I. Understood? Okay, so I will explain how we are getting this relation. How we are getting this relation, I will explain that. Right? Okay. So we know that I can directly tell this one also, okay, but I will explain here. I will explain how we are writing this expression and all, okay, so that you will get clarity. What do you mean by current and what do you mean by current density? Why the current we are treating as a scalar quantity? Why current density is a vector quantity? All these things will be clear. Understood? Okay. Now see here. Now see here. Okay. Now here I am considering a conductor here. I am considering a solid, I am considering a conductor, okay, which is having circular cross section. So I am considering a conductor like this. Let us assume this is a conductor. Understood? Okay. Okay. Yeah. So now let us assume the end of this wire is present somewhere and I have applied some potential difference across this wire. Understood? And let us assume the conductivity of this wire. The conductivity of this wire is sigma. Okay, conductivity of this wire is sigma. So I am assuming that this sigma is not equal to what? Is not equal to infinity. So that means I am not assuming this conducting wire as what? Perfect conducting wire. I am assuming it as this wire is going to have what? Is going to have some conductivity which is not equal to what? Which is not equal to infinity. So that means I am treating this conductor as what? I am treating this conductor as that means what I am saying here is it is not a perfect conductor. So that's what I am saying, right? Okay. Okay. So now see here. Now assume I have applied some potential difference across this conductor. So whenever I apply some potential difference across this conductor, then what will happen? Then what will happen here? So then the current is going to flow. The current is going to flow, or the charge carriers are going to flow throughout this conducting material. Now how we have defined the current here? How we have defined the current? See here you are going to have some free charge carriers throughout this volume of the conductor here. Throughout this volume of the conductor, we are going to have some free charge carriers. Let us assume we are having this free charge carriers here, right? Okay. Okay. Now the number of charge carriers that are, so I am considering this cross section. Okay, so let us say this cross section is A, right? Okay, so the number of charge carriers that are crossing this cross section per unit time is called as what here? Is called as current. Yes or no here? So the number of charge carriers that are crossing this cross section per unit time is called as what? Is called as current. We know that, right? Okay. Now see here. So this is at some instant of time. So now here I have applied some potential difference and all these charge carriers are penetrating through this surface, are flowing through this surface, or I can say they are crossing this surface. Understood? Okay. So let us assume all these charge carriers are crossing this surface here, Okay. See, so once they cross this surface, so then they are going to move like this. Yes or no? Okay, they are going to move like this. So okay, so once they have crossed this surface, then they are going to move in this direction. Understood? Now what I am doing here is at some instant of time here, so that means here, see here, what I am saying here is I have allowed these charge carriers here. To cross this cross section over a time t. Understood? I have allowed these charge carriers to cross this cross section over a time t. Okay, so after some time t here, I am taking a snapshot. So what do you mean by taking a snapshot here? If you take a snapshot, what is happening? I am freezing the time. Yes or no? Okay, so after some time t, I am taking a snapshot. So then how it is going to look like? So here I am considering this cross section here. Understood? Okay, so let us assume after taking a snapshot, so this is the picture I am seeing here. Understood? So that means these are the charge carriers here. Whatever the charge carriers that are present in this volume here, these charge carriers are crossed this cross section in time t or not. Yes or no? What I have done here, I have taken a cylindrical wire. Yes or no? I have applied some potential difference across that wire. Then what will happen? The charge carriers are going to move. In one direction. Understood? So the number of charge carriers that are crossing the cross section per unit time is called as current. Okay. So now I have allowed these charge carriers to cross this cross section over a time t. Understood? So after some time t, what I have done here, I have taken a snapshot. That means I am freezing the time, right? So I am freezing the time. So at that instant of time here, whatever the charge carriers that have crossed this cross section, they are going to present in this region or not. Yes or no? Previously there are no charge carriers in this region. Okay, all the charge carriers I have assumed present in this region. So once I have applied the potential difference, then all the charge carriers starts crossing this cross section. So after some time t, I have taken a snapshot, then I am seeing this picture. So that means whatever the charge carriers that have crossed this cross section, they are present now in this region or in this volume. Yes or no here? Yes or no? So whatever they have crossed this cross section, they are going to present in this region, in this volume. Yes or no? After some time t. Yes or no here? So after some time t, what I am doing? I am taking a snapshot. That means I am freezing the time. So at that instant of time, this is the picture I am seeing. So that means whatever the charge carriers that are present within this volume, so those charge carriers have crossed this cross section in time t. Understood? Have you understand this point here clearly? Tell me here. Alok Kumar, Paras Moon, tell me. Have you understood what I am saying? Have you understood this point? So these are the charge carriers that have crossed this cross section within time t. After time t, if you take the snapshot, you are going under after time t, if you take the snapshot, so this is the picture you are seeing. So that means whatever the charge carriers that are present within this volume have crossed this cross section in time t. Yes or no here? Have you understood this point? Tell me here. Yes? Okay, Parasmoon, yes sir. Alok Kumar, understood? Tell me here. Yes? Okay, very good. Okay, so now see here. So I can write here the number of charge carriers. Number of charge carriers that have crossed the cross section, or I can say that have passed through the, okay, that have crossed the cross section, A within time t. Okay, so is equal to what here? Is equal to the charge carriers that are present within this volume. So let us say this volume is V here. Okay, so this volume I am considering as V. So what is the total number of charge carriers? If I want to determine the total number of charge carriers that are present within this volume here, how you can write here? See, these charge carriers are present throughout the volume. So let us consider the charge density. As rho V. So that is the charge carriers that are present per unit volume. Okay, so this multiplied by what? This multiplied by this total volume. So what is the volume of this region here? So let us say the distance from here to here. Is x here. Let us say the distance from here to here is x, and this is the area. Understood? So what is the volume of this region now? Tell me. This is area, right? So this is the area of cross section, and this is x, right? Now what is the volume of this region? I am just writing the number of charge carriers that have crossed the cross section A within time t. So whatever the charge carriers that have crossed this cross section will be equivalent to what? Will be equivalent to the charge that is present within this volume. So the charge that is present within this volume, I am writing it as what? Charge density, that is the number of charge carriers that are present per unit volume multiplied by what? Multiplied by this volume. Okay, so now what is the volume of this region? This is the area and this is x, this is length. Understood? So x into what? X into A will give you what? Will give you the volume of this region or not? Yes or no here? Yes or no? Parasmoon, Alok Kumar, tell me. Okay, so rho V into volume here, rho V into volume, right? Okay, so volume of this region. So this volume is nothing but what? Volume is nothing but x into what? X into A, x into A, right? Okay, so this is the charge that have crossed the cross section within time t, within time t. Okay, so now see here the number of charge carriers. Now the number of charge carriers that have crossed the cross section A per unit time. Per unit time. Number of charge carriers that have crossed the cross section A per unit time or per second. So then this is nothing but what? The number of charge carriers that are crossing the cross section per unit time is defined as what? Is defined as current. Yes or no? So this is equivalent to what here? What you are going to get? See, these are the charge carriers that have crossed the cross section within time t. Now if you want the number of charge carriers that have crossed the cross section per unit time, then what you have to do? Tell me what you have to do. So these are the charge carriers that have crossed within time t. Now if you want number of charge carriers that have crossed per unit time, then what you have to do? Tell me what you have to do here. You have to divide this with what? With t, with time. Yes or no? Okay, so what you are going to get? Rho V into what? Rho V into x into what? X into A divided by what? Divided by t. Okay, so this is called as what? This is what we have defined as current. Okay, so this is nothing but the number of charge carriers that have crossed the cross section per unit time, understood? Okay, or per second, right? So this is the current here. So now see here, if you observe here, so this I is equal to so rho V into A into what? X by t. Okay, so x is nothing but what? X is nothing but the length here. Yes or no? That means displacement from here to here. Understood? T is nothing but time. So displacement by time is nothing but what? Is nothing but velocity. Yes or no here? So x by t will give you what? Will give you the velocity, right? So this is nothing but velocity. This is nothing but velocity. Okay, I am representing this velocity like this. Okay, velocity v. So that means I can write I is equal to what? I is equal to rho v into what? Rho v into A into what? A into v. Understood? So this is the expression for what? This is the expression for current. This is the expression for current, right? Okay. Now what do you mean by current density here? What do you mean by current density? What do you mean by current density? I is nothing but the number of charge carriers that are penetrating through the surface per unit time. Next, current density means what? The current per unit area. So that we call it as a current density. So current density will represent with J. So since we are considering the current density through the conductor, so we are calling this as a conduction current density. Okay, so that's why I am representing with subscript C. So conduction current density JC is equal to what? Is equal to, I can write this as what? I by A. So which is equal to what? Which is equal to rho V into what? Rho V into V. See, this subscript V represents volume here. So this represents rho V represents the volume charge density. So this V represents what? Velocity. Understood? Okay. So that means JC is equal to what? JC is equal to what? Is equal to rho V into what? Rho V into V. Understood? Okay. So now tell me the velocity here. Velocity is a vector quantity or scalar quantity? See here, rho v is a charge here. Charge is a scalar quantity, right? Okay. So v is nothing but velocity. V is nothing but velocity, right? Okay. So this velocity is a vector quantity or scalar quantity? Tell me here. Parasmoon, Alok Kumar, tell me. V represents the velocity. So V is a vector quantity or scalar quantity? Tell me here. Parasmoon, Alok Kumar. Tell me here. Is a vector quantity. So that means V is a velocity. Velocity is a vector quantity. So that means I can represent this as what? I can represent this as V bar. I can represent this as V bar. And rho V is a scalar quantity. So scalar multiplied by vector must be a what? Must be a vector. So that means this conduction current density must also be what? Must also be a vector quantity. Must also be a vector quantity. Yes or no? And what is the direction of this current density here? The direction of current density is same as what? Is same as the direction of what? The direction of velocity. The direction of velocity. Understood? Okay. So that means Z bar. So that is conduction current density is what? Is a vector quantity. Is a vector quantity. And the direction of Z bar. The direction of Z bar is same as what here? Is same as the direction of what? The direction of velocity. The direction of velocity. Understood? Okay. So in EDC here, in EDC you will study that this velocity Vd this is the velocity acquired by the charge carriers whenever you apply some potential difference across the conductor. Yes or no? So this velocity generally we call it as a drift velocity. We call this as drift velocity. So if you are getting the velocity because of what? Because of some applied force. Okay, so then that velocity is called as what? Is called as drift velocity. So this drift velocity is equal to what? Is equal to mu times of what? Mu times of E bar. Here mu represents what? Mu represents mobility here. Mu represents mobility. Okay, it is not permeability, right? So here mu represents mobility. So Vd is equal to mu into E bar. So here Z bar here, JC bar is equal to what? Rho V into what? Rho V into mu into what? Mu into E bar. Now if you consider rho v into mu into E bar here. So this rho v into mu is called as what? Is called as conductivity. Will give you what? Will give you the conductivity of the conductor. So rho v into mu is nothing but conductivity. So this conductivity multiplied by what? Multiplied by E bar. So JC bar is equal to what? JC bar is equal to sigma into what? Sigma into E bar. Sigma into E bar. So already I have told that sigma is not equal to what? Sigma is not equal to infinity. Understood? Okay. So under that condition, what we are getting here? JC bar is equal to what? Is equal to sigma into E bar. So this is the conductivity. So this conductivity is depending upon what? This conductivity is depending upon volume charge density, and also it is depending upon the mobility of the charge carriers. And also it is depending upon what here? Mobility of the charge carriers. Understood? So if you consider a semiconductor here, if you consider a semiconductor for electrons the mobility will be more when compared to what? When compared to protons. Yes or no? Okay. Okay. Yeah. So in that manner we can determine what? We can determine the conduction current density. So JC is equal to what? JC is equal to sigma into E bar. So for any conducting material, this volume charge density and this mobility of charge carriers will be what? Will be constant. It depends upon the material here. If you consider an iron material, or if you consider some silver material, okay, so it is going to vary. Yes or no? The volume charge density is going to vary, and the mobility of charge carriers is also going to vary. Understood? So this conductivity is going to depend upon what? Is going to depend upon the material, the conducting material that you are using. Understood? Okay. So based upon that material property, this conductivity is going to change. But for a given conducting material, this sigma is going to be what? This sigma is going to be constant. Okay, so if sigma is constant for a given conducting material, then Jc is proportional to what here? Jc bar is proportional to what? Jc is proportional to what? Jc is proportional to electric field. Jc is proportional to electric field. Understood? Okay, so Jc is proportional to electric field, and whenever you are equating these two, so you have to introduce the proportionality constant. That proportionality constant is nothing but sigma. So sigma into E. So Jc equal to sigma into E is called as what here? Is called as the generalized form. This is actually called as what? This is actually called as Ohm's law here. This is actually called as Ohm's law. Understood? So from here only you got I equal to V by R and all these things, right? Okay, see here the units here, the units of Jc, the units of Jc is nothing but what? Ampere per meter square, and the units of conductivity is nothing but what? Mho per meter, and the electric field units are nothing but what? Volt per meter, volt per meter. Yes or no here? Okay. Yes. Okay, so here meter square will get cancelled. So ampere, so here you are having, okay, what I am doing here is, so I am sending this ampere to this side here. If I send ampere to this side, then you are going to get volt by ampere, and this mho if I send to this side, then it will become 1 by mho. So 1 by mho is nothing but what? Is nothing but 1 by mho is nothing but resistance. Yes or no? So V and ampere is the units for what? Units for current. So V by I is equal to what? Is equal to R. Yes or no? So from where we are getting here? So this is nothing but V is proportional to what? Or not V is proportional to, you have to tell I is proportional to what? I is proportional to what? Here, from here we are having I is proportional to V. I is proportional to V. Understood? Okay, so from here only, from this basic relation only, we got all these laws here. Okay, so this is actually called as what? This is actual form of what? This is actual form of Ohm's law. So from here only we got this Ohm's law here, whatever you are using in circuit theory or network theory, in analog electronics, in all the other subjects. Okay, so whatever you are using Ohm's law, so the basic Ohm's law or actual Ohm's law is nothing but what? Is nothing but J is proportional to what? J is proportional to E, right? Okay. Conduction current density means what? Here the current is flowing through what? The current is flowing through the conductor. So if the current is flowing through the conductor, that's why we are representing it as conduction current. Okay, so why I am specifically mentioning it as conduction current, that will be clear once I discuss about modification in Amperes law. Okay, so all those things will come later. So there you will understand why I am specifically mentioning it as conduction current, right? Okay, okay. Yeah. So since here the current is flowing through the conducting material, we are considering the current flowing through the conducting material, so that's why we are calling it as conduction current. Okay, so there is no other specific reason for that, right? Okay, so but why I am specifying this as a conduction current, that will be clear as we proceed into the subject, right? Okay, okay. Because we are having some other currents also, we are going to deal with those currents also. Okay, so in order to differentiate that current and this current, I am representing this specifically as conduction current. Okay, okay. Yeah. So I hope this is crystal clear here, right? Okay, so now what we have understood here is we have started from here and we have gone somewhere, right? Okay, so come to our lecture here. Okay, so Jc bar is equal to what? Jc bar is equal to rho V into what? Rho V into V bar, right? Okay, okay. So here since velocity is a vector quantity, this Z bar is also what? This Z bar is also a vector quantity. Z bar is also a vector quantity, right? Okay, okay. So that means this Z bar here, this Z bar will give you what? Will give you the current penetrating per unit area. Yes or no? Z bar is nothing but what? Current density. So current per unit area. So that means Jc bar is going to give you current penetrating per what? Current penetrating per unit area. Current penetrating per unit area. So current means what here? The number of charge carriers that are penetrating through a given surface per unit time per unit area is called as what? Is called as current density. Okay, so current means the number of charge carriers that are penetrating through a surface per unit time. Okay, that is called as current. What do you mean by current density? The number of charge carriers that are penetrating through a surface per unit time per unit area is called as what? Is called as current density. Understood? Okay. Okay, yeah. Okay, if you have understood this one, that is fine here. Okay. Okay. Now see here. Now see here. Now so that means here, see. So that means here the velocity of the charge carriers is in this direction. The velocity of the charge carriers is in this direction. So that means the velocity is in this direction here. The velocity is in this direction. So if the velocity is in this direction means z bar is must also point in which direction? The direction of z bar and the direction of v bar must be same. So that means the current density must also point in the same direction. The current density must also point in the same direction. Yes or no? So current density will give you the number of charge carriers that are penetrating per unit area, per unit time. Okay, the number of charge carriers that are penetrating per unit time, per unit area, or I can simply say the current penetrating per unit area. Okay, so this Z bar is going to give you the current penetrating per unit area. Okay, now if I consider a small differential area here, if I consider a small differential area, okay, if I consider a small differential area dA bar, if I consider a small differential area dA bar, then how to represent the current penetrating through this small differential area dA bar here? Tell me. If you have understood, the flux concept, whatever I have explained previously. Okay, so if you have understood flux concept clearly, then you would give the correct answer for this question. So what I am asking here is how to represent the current penetrating through this small differential area dA bar. Z bar is the current penetrating per unit area. Now I want to determine, or I want to write the current penetrating through this small differential area dA bar. How you can represent here? Tell me. How you can represent that? Tell me. Mathematically, how you have to represent that? I have explained already about flux here, how to represent the flux through any surface, yes or no? Okay, so if you are having any surface here, okay, so the number of field lines that are penetrating through any surface, is called as flux, and I have explained how to represent this flux through any surface and all these things, right? Okay. Okay, now tell me here, how to represent the current penetrating through this small differential area dA bar. Tell me. Okay, so Z into dA, not into dA. See, whenever you want to represent some field that is penetrating through any surface, what you have to use? You have to use the dot product. See here, if you are having the surface here, so this is what I have explained here. I am saying this many times here. Always these basics are very important. So if I consider some surface area, so if you want to determine the field that is penetrating through this surface here, so the field penetrating through any surface is called as what? Is called as flux through that surface, Now if I consider this vector field as F bar, and if I consider a small differential area, dA bar here, now if I want how much of this vector field is penetrating through this small differential area dA bar, then what you have to use? You have to use the dot product between F bar and what? And dA bar. Right, so F bar dot dA bar will give you the field penetrating through this small differential area dA bar, right? Okay, see the direction of vector field, okay, the direction of vector field is pointing in upward direction, and what is the direction of this small differential area here? So the direction of the small differential area will also point in which direction? It is also pointing in upward direction. Yes or no? Let us assume it is pointing in upward direction. Understood? Okay, so then F bar dot dA bar will give you the flux through what? The flux through this small differential area dA bar. Then if you want the total flux through this total surface area, then what you have to do? You have to integrate throughout this surface, right? Okay, so all these things I have explained here. See, again and again, it is not possible for me to explain each and everything again here. Okay, okay, okay. So here the current penetrating through this small differential area dA bar, how you can represent? So Z bar dot what? Z bar dot dA bar. Z bar dot dA bar will give you the current penetrating through this small differential area dA bar. Through this small differential area dA bar. Understood? Z bar represents the current penetrating per unit area. Now if you want to determine the current penetrating through this small differential area, then what you have to do? You have to do the dot product between these two vectors. Okay, so that's what I have explained here, right? Okay, in the previous classes I have explained all these things, right? So now if I want the current penetrating through this total surface area, if I want the current penetrating through this total surface area, then what you have to do? You have to integrate throughout this surface. You have to integrate throughout this surface. So then you are going to get what? You are going to get the current penetrating through this surface area. So the current penetrating through this surface area, we call it as what? We call it as I. Okay, so I is equal to what? I is equal to double integral what here? Double integral Z bar dot what? Z bar dot dA bar. Double integral Z bar dot dA bar. Understood? Okay, so now if you observe here, I is equal to double integral Z bar dot what? Z bar dot dA bar. So that means Z bar dot dA bar is the dot product, between Z bar and dA bar. So what is the resultant of dot product here? The resultant of dot product is a scalar quantity or vector quantity? Tell me here. The resultant of dot product is a scalar quantity or vector quantity? Tell me. Parasmoon, Alok Kumar, tell me here. The resultant of dot product is a scalar quantity or vector quantity? So the resultant of dot product is what? Is a scalar quantity. Understood? And the resultant of this dot product is nothing but what? Is nothing but I. So that means I is what? I is a scalar quantity. Yes or no? Okay. So this is also I have specified here. Everything here, whatever I am explaining now, okay, so the base of this one is present in the previous lectures, right? Okay, so if you don't go through that previous lectures, okay, you are going to get many doubts here, right? Okay, so for that I am helpless here. So you have to compulsory, it is must here. If you want to learn this subject, you have to go through the previous lectures and you have to understand those basics clearly. Okay, so then only you can understand each and everything very crystal clear manner. Okay, so here I is what? I is a scalar quantity. Whereas current density is what? Current density is a vector quantity. And the direction of current density is same as what? Is same as the velocity of the charge carriers, right? Okay, right? Chaudhary, scalar, very good, right? Okay. Okay, so here I have proved that the current is what? The current is a scalar quantity, whereas current density is a vector quantity. Understood? Okay, so now that means I can represent, I have explained you how to represent this current in terms of what? In terms of current density, So that is I is equal to double integral Z bar dot dA bar. So this is how you can represent the current in terms of what? In terms of current density. Understood? Okay. So now coming to Amperes law. Okay, so see here, coming to Amperes law. So we have seen that the circulation of B field around any closed loop is equal to what? Mu times of what? Mu times of I enclosed or I penetrating, right? Okay, so now how you can represent this I here? How you can represent I? So mu into what? I is nothing but double integral J bar dot what? J bar dot dA bar. So the circulation of B field around any closed loop you can represent in this manner. Okay, so this we call as a integral form of Amperes law. So we call this as what here? Integral form. See, I have forgot to represent the subscript here. Okay, so generally in books also they won't represent the subscript here. You have to understand this as conduction current density. Understood? So in order to make you understand that this is conduction current density, I am representing with subscript C. Okay, okay. Generally in books they won't represent all the subscripts and all, right? Okay, okay. So this is integral form here. This is integral form of what? Integral form of Amperes law. Right. Now see here, I can so we know the relation between B and H here. So what is the relation between B and H here? B is equal to what? B is equal to mu into what? Mu times of H. B is equal to mu times of H. So what are the units of B here? What are the units of B? Units of B is nothing but Weber per meter square. And what are the units of mu here? Permeability. What are the units of permeability? Henry per what? Henry per meter. And what are the units of H here? What are the units of H? That is magnetic field intensity. The units of H is nothing but ampere per meter, right? Okay, so for mu it is Henry per meter, Henry per meter, and for H it is ampere per meter. Okay, so these are the units of these parameters. Understood? Okay, so B you can replace with what? B you can replace with, if you replace B with mu into H bar, so then here mu and here mu will get cancelled. So therefore you can write circulation of H field around any closed loop is equal to what? Is equal to double integral JC bar dot what? JC bar dot dA bar, right? Okay. So you can represent either in this manner or you can represent in this manner. Understood? Okay. Okay. So now see here. Now for this one, if I apply here, so let us consider this LHS side here. This LHS side. Circulation of H bar dot dl bar. So for this LHS side, if I apply Stokes theorem, okay, so if I apply Stokes theorem, then how I can represent this one here? So from Stokes theorem, I can represent this closed loop line integral into what? Into surface integral. Yes or no? I can represent this one as a, by applying Stokes theorem, I can represent this as a double integral what? Double integral del cross H bar dot what? Dot dA bar, that is equal to what? That is equal to double integral JC bar dot what? Dot dA bar. Understood? Okay, so the surface area on both sides will get what? Will get cancelled. So whatever the surface area that you are mentioning on the left hand side, right hand also the same surface area. So this surface area will get cancelled on both sides. So then you can write this as what? Del cross H bar is equal to what? Is equal to JC bar. Del cross H bar is equal to JC bar. So this is the differential form. This is the differential form, or this is the differential form, or what? Differential form or point form of Amperes law, Okay, so curl of H bar is equal to JC bar, right? Parasmoon, what you are asking here? Mini electrician, sir, when will Banu sir will continue his lecture? Is he all right? He is taking medications, and soon he will get all right. Okay, so I hope soon he will take the classes. Okay, right? Okay, mini electrician. Parasmoon, what you are asking here? Have you thought B equal to mu H? What I have to thought here? B equal to mu H. This is the relation between what? Magnetic flux density and magnetic field intensity. So B is equal to mu H. What I have to thought in that? Tell me here, Parasmoon, what you are asking? So this is the relation between what? This is the relation between magnetic flux density and magnetic field intensity. So that is B is equal to what? That is B is equal to mu into H, right? Okay. What is your doubt here, Parasmoon? Be specific here. Right? Okay. Don't hesitate to ask any doubts here. If you are having any doubts, please ask me, right? Be specific with your doubt. So that's what I am saying, right? Okay. So this is the differential form or point form of Amperes law. This is the differential form or point form of Amperes law. Okay. Okay here. So what this is saying here? So what do you mean by curl here? What do you mean by curl? I have told that the circulation, it is a measure of what? Curl is nothing but it is a measure of the circulation of the vector field about any point. Okay, the circulation about any point is nothing but what? Is nothing but curl. So what do you mean by curl? So it is a measure of how much of the vector field is circulating about a given point. So the circulation of H field about a given point is equivalent to what? Is equivalent to the current density at that point. Current density at that point. Understood? Okay. So if you are having any circulation about any point, means at that point there must be what? There must be a source. There must be a source of that field here. Okay, so here the field is nothing but H bar. So if you are having any circulation of the vector field about any point, if you are having circulation of H field about any point, means at that point what must be present here? At that point there must be a source of what? There must be a source of this H field. So what is the source of that H field here? Is nothing but what? Is nothing but current. Okay, is nothing but current density at that point. Understood? Okay, so if the current density at that point is equal to 0, then the circulation of the vector field about that point will also be equal to what? Will also be equal to 0, right? Okay. 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 So finally we got Amperes law. We have expressed Amperes law in integral form. So that is circulation of B field is equal to mu into double integral Z bar dot what? Z bar dot dA bar, right? Okay. Next, or you can write the expression as circulation of what? Circulation of H field around any closed loop is equal to what? Is equal to a double integral Z bar dot what? Z bar dot dA bar. Next, this is integral form here. This is nothing but integral form. So in differential form, we can write this as a curl of B bar. Curl of B bar is equal to what? Mu into Z bar, or you can write this as del cross what? Del cross H bar is equal to what? Is equal to what? Is equal to Z bar, right? Okay. So these are nothing but what? These are nothing but differential form or point form. Differential form or what? Or point form. Right? Okay. Parasmoon, I was asking whether you have previously taught in lecture about B is equal to mu H. No, here I hope you have known that relation, yes or no? See, while dealing with electric field, I have told D is equal to what? Electric flux density, D bar is equal to epsilon into E bar. Understood? So this is the relation between electric flux density and electric field intensity. And here in magnetostatics, in magnetic field, B bar is equal to what? B bar is equal to mu into what? Mu into H bar. So this is the relation between B bar and H bar, right? Okay. Okay, yeah. So here B bar is called as magnetic flux density and H bar is called as what? Magnetic field intensity, right? Okay. Okay, yeah. Right? Okay. So these are the integral forms and differential form of Amperes law, right? Okay. Okay, Parasmoon, do you have any doubts? Alok Kumar, is it clear? Alok Kumar, are you there? Alok Kumar, are you there? Tell me here, up till now whatever I have thought, is it clear here? Tell me, Alok Kumar, Parasmoon, Chaudhary, tell me. Parasmoon, have you gone through that previous lectures here, basic lectures, whatever I have explained? Until you have gone through those lectures, you won't understand here, that's for sure. Okay, you are going to get the doubts again and again and again and again, that's it. Okay, so please go through that previous lectures here. Already I have given a good number of lectures on basics, right? Okay, so if you don't go through that one, like divergence of flux, concept of divergence, concept of Stokes theorem, concept of how to determine the circulation around the closed loop, and what do you mean by point form, what do you mean by differential form, all these things I have explained here, all these things I have explained. Okay, right? I have already told that this gradient, divergence and curl all are defined at a point, okay. So all these things I have explained here. Gradient is defined at a point, divergence is also defined at a point, curl is also defined at a point, right? Okay, so what do you mean by divergence, what do you mean by curl, what do you mean by gradient, right? So all these things I have explained here. Please here, it is my humble request, please go through the basic lectures here. Understood? Okay, previous lectures. So just at least complete that mathematical part. So coordinate system. So first topic is basics of vectors. Next, coordinate systems you are having. Okay, so after that I have started with the del operator. So after del operator I have started a gradient. I have explained gradient, and then flux I have explained, and then I have explained divergence, and then I have explained circulation, and then I have explained curl, and I have explained null identities, right? Okay, so all these things I have explained here already. Okay, so if you have not gone through those lectures, then I am helpless here, I am helpless. Here, how will we define this point form? This form is called as point form. Why we are calling it as point form? Because the curl is defined at a point, so that's why I am calling it as point form of equation, or we can call it as differential form. Why I am calling it as differential form? If you expand this curl, you are going to get what? Differential operator. Yes or no? So that's why I am calling it as differential form. The curl, divergence, gradient are defined at point, so that's why I am calling it as point form, right? Understood, Parasmoon? So first of all, let me know whether you have gone through that previous lectures here. Parasmoon, tell me. Have you gone through that previous lectures? Tell me. Have you gone through that basic lectures? See this curl operation here, curl operation, this curl is defined at point. Understood? It is defined at a point. So that's why we are calling this expression as point form of Amperes law. Or since if we expand this one, you are going to write this in terms of differential operators. So that's why we are calling it as differential form. Here why we are calling it as integral form here? Because we are representing this law in terms of what? Integration. So that's why we are calling it as integral form. Okay. See, please Parasmoon, please go through that lectures and then you can comment here. Okay. Okay. Because the thing is, if you don't go through that lectures, if you directly attend the lectures, you don't understand, that's for sure. Okay, that's what I am saying again and again and again, right? Okay, so EMT is not like you can come at any instant and you can understand instantly. It is not like that. You must need some basics in order to understand the subject. So if you are not familiar with those basics, so that's what I am saying, you are going to get again and again and again and again, you are going to get the same type of doubts. Okay, but here I cannot explain again and again and again the same things here, right? Okay, already it is available in YouTube, each and every lecture is available, go through them. Okay, so if you are getting any doubts, you can contact me through Telegram channel. Okay, that means previous lecture doubts. If you are having any doubts in the previous lectures, you can contact me through Telegram channel. Okay, okay. So in the live session, if you are getting any doubts, you can ask me in the live chat. Okay, for previous lectures, you can ask me in Telegram channel, right? Okay, okay. Okay, right. What is the definition of Amperes law in point form? Okay, write down here. The circulation of H field about a given point is equivalent to the current density at that point. Note down. Note down here, Parasmoon, note down. The circulation of H field about a given point is equivalent to what? Is equivalent to the current density at that point. See, I have explained the same thing while explaining Gauss law also. So there we got the point form like divergence of E bar is equal to what? Is equal to rho V by epsilon. So there what I have told here. So if there exists any divergence of electric field at a point, means at that point what must be present? At that point there must be a source of that electric field, that is nothing but charge density. Understood? Here also the same thing or not? So if you want to determine if there exists any circulation of H field about a given point, means at that point what must be present? At that point there must be a current density. Understood? So if there is no current density, then the circulation of H field at that particular point will be equal to what? Will be equal to 0. Right? Okay. You can correlate in that manner here. Right? Yes. Parasmoon, you have not given the answer for my question. So that is, have you gone through the previous lectures, that is basic lectures where I have explained del operator gradient, divergence and curl, all those things I have explained. So have you gone through those lectures? First of all, let me know. Tell me, Parasmoon, tell me. Have you gone through those lectures? Tell me here. I don't think so that you have gone through those lectures. I don't think so. If you have gone through those lectures, then you are not going to get all these doubts. That's for sure. So in order to understand this expression, first of all, you have to understand the definition of curl. So then only you will understand this one, right? When I thought I have attended them at that time. Okay, so you have attended here, but you have understood or not? You have understood those things or not? Have you written proper notes and have you understood all those things? Have you understood all those things? So after class here, after class, you just refer all those previous lectures here. So if you are having any notes, if you have written any notes, okay, so then go through that notes here again, okay, then you can recollect all these things. See, just listening the class doesn't help you. If you write a proper notes, then only it is going to be very much helpful. So whenever you are getting this type of doubts, then you can refer the previous class notes, okay, so then only that doubts will be clarified, right? Okay, so each and every time I cannot explain the same thing again and again and again, right? Okay, okay, okay. So please go through that previous lectures here. Please go through that notes again, okay. So still if you are having, if you feel any doubt, you can happily ask me tomorrow here, okay. So don't hesitate to ask, please ask me doubts, okay. If you are having, if you are having any doubts, you can ask me tomorrow, right? Okay, so please revise those lectures, whatever I have explained. Please revise that notes here once again, okay. Okay, so with this I am winding up the session, right? Okay, so tomorrow exactly at 4 p.m. again, tomorrow exactly at 4 p.m. we are going to have the session on EMT, right? Okay, so tomorrow exactly at 4 p.m. we are going to meet again, right? Okay, so with this I am winding up the session for today. So tomorrow we'll meet exactly at 4 p.m. right? So until then, take care, bye bye.